Hi, my name is Eric, and this is an introductory video to help new users get started using continuity. We will introduce several important features of continuity by generating a simple model of a left ventricle and performing a simple biomechanics problem. Continuity is a problem-solving environment for multi-scale modeling in biomechanics, biotransport, and electrophysiology. It is freely available for academic use under license from UCSD and downloadable at the Continuity download page. Several new updates are released per year. Although continuity is generic and application neutral, we have developed it to support our research on cardiac physiology and pathophysiology, and therefore it is particularly well adapted to multi-scale problems in cardiac electrophysiology and biomechanics, including coupled multi-physics, multi-scale models of the heart. In this introductory guided tour, we focus on example applications in cardiac modeling. Because multi-scale biological models are most often valuable when used in close association with experimental investigation, continuity incorporates extensive facilities for analyzing and fitting measured data, including biomedical images, and the ability to author and dynamically compile component models, such as constitutive equations for tissue properties, systems models for cellular dynamics, for example, ionic current models in electrophysiology, material coordinate definitions, and lumped parameter models of circulatory hemodynamics. A key objective and design priority of our continuing continuity development efforts is that every aspect of a problem or simulation that you would consider to constitute the mathematical model or its biological parameters should be data that can be easily shared and reused. For that reason, too, there is also a public continuity model database that you can access directly from within the continuity client. At its core, continuity is a PDE solver that implements finite element methods for nonlinear mechanics, reaction diffusion, and monodomain problems. A typical multi-scale problem in continuity spans 3 or more scales, typically comprising a system of ODEs at each point in the physical domain, representing a network of biochemical or biophysical interactions, a constitutive law representing physical properties of the system that spatially couple these pointwise networks, a system of PDEs representing the conservation law governing the physics over the anatomy of the system, and a model of boundary conditions representing the interactions of the system with neighboring structures. For example, in a typical cardiac biomechanics problem, ODEs represent dynamic Markov models of myofilament activation and interactions in the cardiac myocyte. The constitutive equations describe the three-dimensional anisotropic mechanical properties of the tissue with respect to local structural axes and how the myofilament interactions modify them dynamically. The governing PDEs for force and momentum balance are solved for an anatomic model of the heart subject to boundary conditions developed by a lumped parameter model of the whole circulation. Similarly, a cardiac action potential propagation model comprises equations representing the dynamics of individual ion channels and whole cell ionic currents and potentials as systems of ODEs that are spatially coupled via the monodomain PDEs by anisotropic conductivities and subject to boundary conditions representing the passive current spread through the torso. Continuity can be downloaded for Windows, Mac OS X, and Linux platforms from the Continuity download page. Installation uses industry standard mechanisms specific to each platform, such as DMG files for the Mac OS and an MSI point-and-click installer for Windows. You can also see the help pages for detailed installation instructions. When you run Continuity, if you have not yet done so, you will see the option to register yourself as a user from the splash screen. You don't need to register to install or use Continuity, but access to the model database does require a registration key as it makes use of federally supported internet resources at UCSD and the San Diego Supercomputer Center. We encourage you to register and provide us with information about your research interests so that we can improve the tools for your needs and provide useful statistical information to our federal sponsors. Continuity consists of a client and a server. The client serves as the graphical user interface, and the server carries out the numerical calculations for simulation and problem solving. The installation process installs both on your computer. When you launch Continuity, the splash screen appears and gives you the default option of running the client and server together on your local machine so that they behave as a single application. However, you can also use the Continuity client to connect to a remote server running on another host, including a Linux cluster. There is no need for the client and the server to be running on the same OS platform. The server has dynamically compilable and loadable numerical analysis functions for mesh handling, data fitting and image handling, and biomechanics, electrophysiology, and transport processes. Correspondingly, the user can load client-side components corresponding to these separate modules that appear as new menus in the GUI client. Indeed, you will see the option to load certain modules directly in the splash screen. By default, only the mesh module is selected. You don't have to decide at this stage which module you want to use. You can always load modules at any time. The mesh module is the most commonly used module in Continuity, which is why it is active by default when you start Continuity. One powerful and uncommon feature of Continuity is the ability to create and use meshes using curvilinear coordinate systems, such as cylindrical polar or spherical polar coordinates, as an alternative to rectangular Cartesian coordinates. There are 4 built-in world coordinate systems in Continuity, including Cartesian coordinates. Investigators working on ventricular mechanics in the 1960s and 70s, including Streeter, Hanna, and Mirsky, approximated the left ventricle as nested ellipses of revolution. Here we show data from Streeter and Hanna from 1973, who fitted truncated ellipses of revolution to measurements of left ventricular epicardial and endocardial major and minor axis dimensions in canine hearts, isolated and fixed under various loading conditions. Just as using cylindrical coordinates simplifies the description of tubular objects, the natural coordinate system for ellipsoidal shapes is prolate spheroidal coordinates, lambda, mu, and theta. In prolate spheroidal coordinates, the longitudinal or mu coordinate forms families of ellipses, each with a common focal point at x equals d. The radial or lambda coordinates form hyperbolae. Streeter and Hanna showed that the focal distance is remarkably constant both between the epicardial and endocardial surfaces and between systole and diastole in the dog left ventricle. Based on their data, we will create a prolate spheroidal mesh in Continuity using a focal length of 3.7 centimeters. From within the Continuity Mesh menu, choose Edit, Coordinates, and then select Prolate Spheroidal in the pop-up menu. Enter 3.7 for the focus position, and then click OK to submit. From the major and minor radii reported by Streeter and Hanna, the focus, and the equations for prolate spheroidal coordinates, we can easily compute the lambda coordinates of the epicardial and endocardial surfaces, as shown in the table. Streeter and Hanna also defined a truncation factor as the fraction of the equator apex distance between the base and the equator. Their estimate of nearly 0.5 translate to a mu coordinate at the base of 120 degrees. We'll use these values to specify nodes of our mesh, but first we need to choose a suitable finite element basis function to interpolate the geometric variables. Unlike finite difference methods, which discretize a continuum into a finite number of points and approximate the governing differential equations using differences, finite element methods approximate the continuum using a finite number of functions, usually piecewise polynomials spanning subdomains or elements, with parameters defined at the vertices or nodes. The governing equations are represented using a weak integral form that gives rise to sums instead of differences. This facilitates the finite element assembly of the global system of equations by addition of the element matrices representing the discretization of the integral equations over each subdomain. Continuity supports a variety of basis functions for isoperimetric finite element interpolation. The simplest type of elements are piecewise linear Lagrange elements. Note that within each element there is a local finite element, or xi coordinate, that also varies from 0 at the first node to 1 at the second. The parameters of the linear interpolation are the values u1 and u2 of the function at the nodes, and thus the basis functions phi1 and phi2 are the corresponding linear functions that, when multiplied by u1 and u2 respectively and added together, result in the linear interpolation between u1 and u2. Note also that the term isoparametric here refers to the fact that rather than interpolate a variable y as a function of geometric variables x, we interpolate both as functions of xi, so that y of x does not itself need to be a function. The major advantage of finite element basis functions, such as linear Lagrange interpolation schemes, is that, since the parameters of the interpolation are the value at the global nodes shared by adjacent elements, continuity of interpolated variables between neighboring elements is automatically ensured. Simply by taking products, we can use these simple 1D linear Lagrange basis functions to generate 2D quadrilateral bilinear Lagrange elements as functions of xi1 and xi2, and 3D hexahedral trilinear Lagrange elements as functions of xi1, xi2, and xi3. We are now ready to make our first mesh in continuity using the prolate spheroidal coordinates we calculated from Streeter and Hanna's data. We will build a simple truncated, thick-walled prolate spheroidal mesh with a single linear 3D element. First, we need to select a trilinear Lagrange 3D basis function. Using the mesh edit basis command, select Lagrange basis function 3D linear 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 with 3 integration or collocation points for xi1, xi2, and xi3. Click Add and OK to submit. Selecting Mesh Edit Nodes brings up a large form where we can define the nodal values of geometric coordinates and other predefined variables, such as fiber angles and fields. In our model, coordinates 1, 2, and 3 are lambda, mu, and theta respectively. Even though a trilinear element has 8 element nodes, we only need 4 nodes for this model because it is axisymmetric, wrapping around on itself. We'll see how to handle this when we define elements shortly. Since we only selected one basis function, linear 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 Lagrange, probably already appears at the top of each coordinate column in the nodes form. If not, select it from the menu for all 3 coordinates. Now, click the Insert Node button on the left 3 times, so that there are a total of 4 nodes. Then simply type in the nodal prolate spheroidal coordinates for each node that we computed for the canine left ventricle. Note that the default units for angular coordinates, such as mu and theta, is degrees, but that can be changed to radians using the radio button at the bottom of the form. We will also assign a label to each node, which will be useful later when we define boundary conditions. To do this, enter a text string in the text entry field at the top of the form next to the Edit button and to the right of the node number display. Use the labels apex endo, base endo, apex epi, and base epi for nodes 1 through 4 respectively, as shown in the table. Note that you should always press Enter or Return after each field so that it can be saved. The underscore in the label serves the special purpose of enabling a compound label, which we will take advantage of later when we refine the mesh. The grayed out fields next to the unchecked boxes for each nodal parameter are not needed for linear elements. They represent derivative parameters that we will use later for higher order Hermite interpolation schemes. The Import-Export Graph button on the left panel provides a convenient way to import or export the nodes as tab-delimited tables that can be viewed or edited in the Continuity Table Manager or a spreadsheet program, such as Microsoft Excel. Click OK to submit the nodal coordinates and labels. Next, we'll use the Edit Elements command from the Mesh menu to create one element. By entering the 8 node numbers for each trilinear element, we both define the elements and the directions of their local xi coordinates. The graphic in the form helps remind us of the numbering convention in which nodes are entered starting at xi 1, 2, and 3 equals 0, and ending with the node at Xi1, 2, and 3 equal 1. By convention for meshes defined in curvilinear coordinates, we make Xi1 coincide to the extent possible with the polar or theta axis, Xi2 with the longitudinal z, phi, or mu axis, and Xi3 with the radial r or lambda axis, while also trying to keep the Xi coordinates right-handed by convention. Note that this has the odd effect of requiring that Xi1 coincide with the negative theta axis in prolate spheroidal coordinates, because theta is the third prolate spheroidal coordinate by convention, but it is the second coordinate in cylindrical or spherical polar coordinates. However, in this example, Xi1 wraps all the way around, so the order doesn't matter. Hence, following these conventions, the 8 element nodes of our single trilinear element are defined by the 4 global nodes entering the node sequence 1, 1, 2, 2, 3, 3, 4, 4 in the element form for element 1, where we have incremented first circumferentially through Xi1, then longitudinally from apex to base through Xi2, and finally radially through Xi3 from endocardium to epicardium. Note that in this very simple case, our world curvilinear or theta coordinates and our local finite element or Xi coordinates coincide, and both are right-handed systems, though their coordinate order is different. In general, though, we will not be dealing with such simple shapes, so we cannot expect the Xi coordinates to follow along world coordinate axes, though we do generally try to maintain right-handedness. You should also enter a label for element 1, for example LV, into the element label field at the top of the form, and remember to press return. Click OK to submit the elements. Now we are ready to use our new mesh. The Calculate Mesh button on the toolbar is a shortcut to the Mesh Calculate Mesh menu choice. Click OK in the dialog box. Behind the scenes, Continuity also carried out a file send to server command, which updates the Continuity server with any client changes and can be performed using the Send toolbar button. Nothing visible happens yet, but now you can render the mesh as a wireframe or surfaces using the Mesh Render Elements command or the Render Elements toolbar button. There is also a Mesh Render Nodes command. There is a wide variety of graphical rendering controls in the View menu. For example, the View Show Open Mesh command, accessed by this toolbar button, lists the rendered objects and their attributes. The entry field next to Select in the Information tab provides a way to highlight specific elements or nodes. Select the Nodes object from the list of graphical objects on the left to try this. The Mesh List Elements command will give you information on element volumes, faces, and lines. Check that the volume of the wall is being integrated accurately. If necessary, you can adjust the number of Gaussian quadrature integration points in the Edit Basis form to increase the accuracy of numerical integration at the expense of more calculations per element. Although the left ventricular cavity itself is not part of the mesh, there are also ways to integrate the cavity volume bounded by defined surfaces in Continuity. Choose the Mesh List Volume command. This command calculates volumes bounded by a surface surrounding a single origin. To get an accurate cavity volume, we need to place the origin at the plane of the endocardial base. We can use the information in the geometric data table to compute this position. Y and Z are 0, but X is negative and equal to H times A, which is 0.45 times 4.2, which equals 1.89 for the endocardium at end diastole. For XYZ under Define the Origin, enter minus 1.89, 0.0, 0.0. Use the pull-down menu next to the Element List field and you should see your previously defined element label LV. Select it. Choose LV endocardium from the menu underneath Wall, then click the Insert Surfaces button. Then select Epicardium from the Wall menu and Insert Surfaces again. Click OK and the cavity and wall volumes will be displayed. Because the calculation is completely different, the wall volume will probably not be exactly the same as the mesh volume displayed previously, but it should be fairly close. The ventricular muscle fiber architecture has a characteristic pattern in most mammals that is surprisingly conserved. Roughly, the myofibers remain in planes almost parallel to the walls, with helical pitch orientations varying from 60 to 90 degrees counterclockwise from the circumferential axis, which are right-handed helices, in the subendocardium, to minus 45 to minus 90 degrees, or left-handed helix, in the epicardium. This familiar convention for fiber orientation is due to the quantitative measurements of Streeter and co-workers in the 1960s, and for this, fiber orientations reported using these angles are sometimes called Streeter angles. Most models assume that fibers lie parallel to the wall, though some investigators have measured small but significant out-of-plane transverse or imbrication angles, especially near the base and apex, which we will assume to be zero. It is important to remember that cardiac myocytes, which, unlike skeletal myocytes, are not really fibers at all. They are rod-shaped cells with end-to-end and side-to-side junctional connections and branches. Sections cut across the fibers reveal that the myofibers are organized by the paramesial collagen matrix into branching laminar myocardial sheets, approximately 4 cells thick. Their orientations tend to have a greater local dispersion and commonly show bimodal distributions in some regions. But based on the predominant sheet orientations, it is now common in biomechanical and electrical models of the ventricles to use a local orthonormal fiber sheet normal coordinate frame following the work of Legris and colleagues. We will use published measurements of fiber angles to build the material coordinates in our model. These measurements show that muscle fiber and sheet orientations vary transmurally in the dog. A comprehensive analysis of fiber and sheet architecture in the canine ventricles was performed by Legris et al. In 1997. But even with our single-element prolate spheroidal model, we can represent much of the variation in myofiber architecture. For the purposes of demonstration here, we will approximate the measured transmural distributions of fiber angles in our 3D prolate spheroidal model by using the trilinear Lagrange basis functions that you created earlier. Estimated parameters are tabulated here. To enter these values, let's go back to the Mesh Edit Nodes form. Click on the Fiber Angles tab. Then select Linear, Linear, Linear from the Select Basis Number drop-down menu below Fiber Angle. Select Linear, Linear, Linear for transverse and sheet angle as well. Now you will see that extra nodal parameter entry fields are checked. Use the table to enter the nodal value parameters. Continuity uses 4 coordinate systems: global rectangular Cartesian coordinates, y1, y2, and y3, curvilinear world coordinates, theta1, theta2, and theta3, local finite element coordinates, xi1, xi2, and xi3, and local material coordinates, x1, x2, and x3. The Mesh Edit Material Coordinates command in Continuity allows us to define an orthogonal transformation that rotates global Cartesian coordinates at any point in the mesh to the local orthonormal material coordinates. The standard predefined material coordinate transformation in Continuity uses the local xi coordinates as intermediates to create a locally orthogonal body coordinate system with one axis aligned with xi1, one in the xi1, xi2 plane, and the third perpendicular to the other two. These axes are then rotated through the fiber, transverse, and sheet angles to generate material coordinates coinciding with the fiber, sheet, and sheet normal directions. Within the context of continuity, we call this definition of material axis transformation the standard material coordinates model. The equations and parameters of this model have already been defined and are stored in the continuity database. Go to Mesh, Edit, Material Coordinates. If the model shown is not MatCoord standard, hit Cancel in that window. Then within the Continuity client, go to File, Library, Search, and enter MatCoord standard in the top search window. Right-click on the model that was found and select Load. It is important that you select the third option in the pop-up window that appears. Then, if you go back to Mesh Edit Material Coordinates, you should now have the standard material coordinate model equations and parameters. Compile this model under Compile and use C double precision. When the compilation has completed, click OK, then go back and check the parameters to make sure that the fiber angle parameter is set to the fiber angle field. You can change the values of the parameters later without having to recompile the model. Then click OK to exit the model editor. To solve a biomechanics problem, we will first need to refine the mesh to allow for reasonably converged stress and strain solutions. Here, we will refine the mesh into 5 elements longitudinally and 2 transmurally. Select Mesh, Refine, and under New Element per Old Element In, select 1 for Xi1, 5 for Xi2, and 2 for Xi3. Click OK. Then, re-render the mesh after first remembering to use the Mesh Calculate Mesh command. Your mesh should now have 10 elements. Note that the node numbers will have changed, but the labels will be preserved. More importantly, the new nodes will have inherited the labels in a logical way. The new node at the apex will have the label apex. The new nodes at the base will have the label base. The new nodes along the inside surface will be labeled endo, and the new nodes along the outside will be labeled epi. You can use the Mesh Edit Nodes command from the Mesh menu to open the Nodes form and confirm this. The biomechanics module of continuity uses a Newton iterative method to solve the continuum equations of motion for nonlinear, anisotropic, large deformation elasticity problems subject to traction and/or displacement boundary conditions. Various other special features of biomechanics problems, notably viscoelasticity, dynamic active force generation, and boundary conditions generated by circulatory models, can be included too. The necessary governing equations include the nonlinear kinematic strain displacement relations for large deformations, conservation of linear and angular momentum equations from continuum mechanics, a nonlinear constitutive equation for hyperelastic materials, and in the case of incompressible models, the Lagrangian mass conservation law. The weighted residual formulation of the finite element equations uses the Galerkin finite element method, which is equivalent in this case to solving the virtual work integral equations of mechanics. We will now change our basis functions for the undeformed and deformed geometric variables from trilinear to linear bicubic to allow a more continuous and higher order variation of stress and strain transmurally and longitudinally. First, we need to add these basis functions. Go to Mesh, Edit Basis, and select Linear Cubic Cubic under the Hermite menu. The Refine command will automatically generate the correct derivatives we need for the undeformed geometry. Open up the Nodes form again and change the basis functions for coordinates 1, 2, and 3 to linear cubic cubic. Observe that the non-zero parameters that the mesh refinement has calculated and inserted into the form are now active. You can load the biomechanics menu and module using the Add Module toolbar button or from File, Load Modules. First, use the biomechanics update initial conditions from undeformed nodes command to copy the undeformed nodal coordinates and basis functions to the initial conditions tab of the boundary conditions form. Next, we will use the Edit Boundary Conditions form to assign nodal displacement boundary constraints as shown here. The Deformed Coordinate 1 tab can specify constraints on the deformed lambda coordinate. The Coordinate 2 tab specifies constraints on the deformed mu coordinate, and the Deformed Coordinate 3 tab specifies constraints on the deformed theta coordinate. For the node numbers, you can use the labels base.star, apex.star, and base epi, as shown in the table, to specify the list of nodes for each constraint. Note that the .star is a wildcard option that will capture the nodes labeled base epi, apex endo, etc. Next, we can assign pressure boundary conditions using the External Pressure tab of the Boundary Conditions form. In the Element Number field, enter a comma-separated list of the element numbers on the inner surface of the model. These are elements 1 through 5. Next, to select pressure type, select Incremental and assign the pressure increment to the inner faces. For passive filling of the left ventricle, 0.1 kilopascals should work well. Then click OK to submit this form. To specify the material properties, we use the Edit Constitutive Model command from the Biomechanics menu to open the model editor. Here you can edit an existing model or author and compile a new one provided the compilation environment is set up. One model that is in the continuity database is an orthotropic, exponential, slightly incompressible strain energy function of Lagrangian strains, proposed by Usick and McCulloch for canine myocardium, in which the strain energy is a function of strain components referred to local fiber, sheet, and sheet normal material axes. Of course, without recompiling, we can change the 7 parameters of this model, which are an overall scaling coefficient and one coefficient for each of the 6 strain components in fiber, sheet, and sheet normal coordinates that appear in the exponent of this strain energy function. However, we will start with a slightly simpler transversely isotropic exponential strain energy function, in which the fiber direction of the tissue is stiffer than the transverse direction, but there is no difference between the sheet and sheet normal or cross fiber directions. This can be found in the continuity database by selecting File, Library, Search, and searching for BMTI of Lagrangian strains, comp SymPy. This can be loaded by right-clicking and selecting Load, and then selecting the third option in the Resolve Conflict window. The model has only 5 parameters instead of 8 for the orthotropic model. The last parameter is a bulk modulus of the slightly incompressible term in the model. It is relatively high and penalizes changes in volume as the tissue pressure rises. The higher this number, the less the volume of the tissue will change as the material deforms. A number that is too low can make the solution sensitive to the specific value. As the value gets higher, the solution changes less but can be harder to obtain. We will start with the default transversely isotropic exponential model. Later we will switch to the orthotropic model. Leave the parameters in their default values and click OK. Before we solve the biomechanics problem, we should check that the dimensions of all the array variables in the model are correct to avoid simple computational errors, particularly indexing errors. To do this, go to View, Edit Dimensions, and ensure that All Dimensions Are OK is displayed. If there is a message about variable sizes being too small or too large, click Apply Marked Recommendations to automatically change the allocated sizes of all incorrectly sized variables. If you click Show Details, you can view each variable and its current and recommended sizes. Now, send the data to the server and recalculate the mesh. Now all that remains is to issue the biomechanics solve nonlinear command. If you specify 10 time steps of 1 units each, then 10 previously specified pressure increments, which we said would be 0.1 kilopascals, will be applied, and the final pressure will be 1 kilopascal. Note that the solve form includes stopping criteria for the iterative solver based on the sum of the solution vector increments, the sum of the unconstrained residuals, and the maximum number of iterations. For this problem, the default setting will work, but that is not always the case. If the solution is having difficulty converging, you can relax the stopping criteria by increasing the number of iterations and/or the tolerance for the sum of solution increments and the sum of unconstrained residuals, usually up to 1 times 10 to the minus 2. Decreasing the time step by orders of magnitude is also helpful. I'm going to pause the video here, and you may want to do the same while the solution solves. The next command we will use makes use of a field variable which must have a basis function assigned to it in the nodes form. Open the nodes form again, and under the field vector 1 tab, for field variable 1, choose linear, linear, linear Lagrange. Now that the problem has solved, we can use the biomechanics render surface command. Choose deformed, and under variables, select T, Cauchy stress tensor, to visualize individual components of the stress or strain tensor solutions on specified element surfaces. If you want to change the color, go to View, Show Open Mesh, select the textured field from the rendering order list on the left, then click on the Colors tab to select your color scheme. There are many pre-built models that are ready for the biomechanics solve. These can be found in the Continuity Model database. To access them, go to File, Library, Search. You can try looking for Getting Started BM Trans for the transversely isotropic case, and Getting Started BM Ortho for the orthotropic case. To load them, simply right-click on the title of the model and select Load.